Today we will transition from the topic that we went over in the past four lectures, which is program representation, assembly, and even more assembly. Now that we are done with assembly, we are done with how the program run, we will talk about the next really important part of the computer that actually get overlooked quite a lot in Thailand and is so important to performance and reliability and many things that most places in the world know that this is one of the primary bottleneck in the program, the memory hierarchy, right? So we'll be talking a lot about the main memory because we do a lot of things in the main memory. That's where you store your program. That's where you store your data. That's where you store the stack and the heap, right? And so now I think it's the perfect time to dive into this. It's the perfect time we dive into this. The first thing we have to talk about is what do we want in the main memory? What do we want in the main memory? So let's say you go to Pantip, oh, too old. Uh, let's say you go to like Fortune Town or like IT store, like Banana IT, or even the website that sells the component for your computer. What do you want for your memory? What would be the perfect memory for you? What do you want from it? I mean, let's assume we have a magic. We have magic and we can get whatever we want. What should be the goal? Uh, It should be free, yes, right? I should be able to buy it and afford it. Only doesn't cost me anything. It should be cheap. It should be low cost. It should be fast, right? Zero latency. Anyone heard about this word latency before? Yeah, you want the 8 GB DDR5 or 128 GB in size if possible, right? And that is true, right? Actually, but what do you mean by you don't believe in low latency? Yes, good point. Good point. There's always latency. There's actually this thing called memory wall. We'll talk about this in a bit. But zero latency doesn't exist unless we have black magic, right? Anyone here play online game like Dota 2, League of Legends, I don't know, ROV, I think? The one that kids play these days. I don't know. I back in the day I played a lot of Dota 2. Don't look into my Steam account and how many hours I put into that game. It's embarrassing. I played that a lot when I was at CMU. But anyone here look at the latency before? What do you do and what would happen when the latency is high? So when you type the command ping, anyone have ping a website before? So one thing I can do, right? I can go to command prompt. So this is what I can do, right? It's pain. This is basically what I can do. I can say ping, right? www.google.com, right? Oops, here. It will say, hey, I got a reply in these milliseconds, right? Time. Anyone here want to take a guess? What is this time that you just saw on the screen? Or is it's written down there? What does ping actually do? What it does is basically, let's say you're here, right? Your computer. There's a Google server. When I ping Google, I send an empty packet here so that they reply back here. Is the time, yes, exactly. It's time for me to transfer this many bytes of data. It's not exactly empty, but it's like a it's a data that doesn't require anything except for, hey, please ping me back. So you send it back and forth between your computer and Google. And that's the latency, is the speed. It's the speed, the amount of time it takes to do one thing. Right? So that's the zero latency you want it. So in memory, zero latency means that if I want the data, I want that to have black magic. As I said, you don't believe in low latency, it doesn't exist, and I agree. We want to, if we have black magic, we want to make sure that instantaneously I got my data. I want them to have as big capacity as possible, right? Unlimited capacity. And I want them to be free, right? And I want them to have high bandwidth. This means that I can send many access at the same time. You might have heard about the word bandwidth. Can someone tell me what's your understanding of this word bandwidth? Yes, actually, that's perfect. How much data that you can move in a unit of time. So, latency is different from bandwidth. This is a little bit side topic from today's lecture, but I want to make sure it is clear. Latency is for one thing you're doing, how long does it take? Bandwidth is, given this period of time, how much work can you do? How much data you can move around. So you compare this to like a water pipe system, right? A water pipe system, bandwidth would mean that if I give you 1 minute, how many liters of water can the pipe sustain? Latency means what's the velocity of the water that moves in through this pipe, right? And all of these demand, they actually conflicts with each other, because it's pretty obvious that they conflict with each other. If I want to have big DRAM, I would have to pay more, right? I would have to pay more. If I want more bandwidth, like the one that's available in the GPU, like the HBM2 in the high-end GPU, I would have to pay more. It's actually slower as well. HBM2 is actually can be slower than GDDR6, but it gives you a lot more bandwidth. If I want to have a big DRAM, it would take more time to access, right? So now let's look into the memory technology. All right. So now let's look from the programmer point of view. Earlier is from the consumer point of view when you buy the memory, right? Now let's look at the programmer point of view. Let's say if you want to program something, one thing that you want is when you malloc and you ask for more memory, you should have unlimited memory. That's what we want, right? You also want it to be contiguous. What does it mean? Let's say if I have an array, right, called A that span from A of 0 to A of 999. What can I assume about this location of A0, A1, A2, A3, A4 up to A999? The hint is the word contiguity. What can I tell about A0 and A1, and A1 and A2, and A2 and A3? It will be next to each other, right? It should be contiguous. It can be super annoying. Imagine this. If you don't have contiguity, what it means is you can have random location that is owned by a different program. In the middle here, so you have to break between A of 400 and A of 401. It's totally not next to each other. This can be annoying, right? So for the programmer point of view, you want contiguous address. The programmer will see what we call virtual memory. We'll cover this once we're done with caching, which is today and next Tuesday. All right, we'll talk about virtual memory next, but the OS, the operating system, and the hardware work together to give you this abstraction of the memory. It worked together to give you this abstraction of the memory. And inside the hardware, you have to remember that the main memory, the DRAM that you buy, is a physical thing. It actually has components that go in there to store the electrons. You have to have a way to access them. You have to have a way to actually go in there and access this memory, right? So now let's look into the current memory technology. All right. So let's look into, hey, what do we have right now? How many people buy a CPU for your computer before? Or at least like when you buy a computer, you look at the processor specification. Like, is it i9, i7, i5, and what is the clock of each of the CPU you're buying? Anyone did that before? So if you haven't done so, I suggest you like go to one of the like computer store online and search for processor. There'll be many things listed, right? There's so many specification tied to the processor itself, right? And these are the memory technology that goes into the processor has different type of I guess the way you store the data. One type of the memory technology is called SRAM. These are the cache. Anyone heard about this word before? Cache. When you buy a processor, you might have seen this. Yes. I mean, and that's life, right? Every generation, new chip comes out and it looks amazing on the specs. Um, and that's a good thing. That's a great thing, actually. Every time new hardware comes out, you can run more complex program. Why is that good? Anyone here fear of global warming that it might kill all of us in the next, like, I don't know, 30 years? By the way, that's a big problem. That's a big problem that we all are going to run into. Uh, we can do efficient programming. We can use the program to model the effects of climate change, right? We can apply more accurate model. We can apply more computation to things that we never ever be able to do before because computer were weaker back in the day. Now it's much faster. You can do fancy and cool things. The same thing goes with the GPU, right? If you look at games and how it looked back 10 years ago and now, they would look different. It would look so different. These graphic is so amazing. And in the next 10 years, it's gonna look even more amazing, right? So that's the advance in technology. And anyway, so if you buy the processor before, you might have seen this word called cache. Today, we will talk about what is a cache. Cache is SRAM. They are fast, but they cost a lot. They are fast, but they cost a lot. The one that you have in your memory is called, the technology is called DRAM. They are cheaper, but they're slower. And in SRAM, it consists of this particular slide won't go into your exam. This is more of the computer engineering side of thing rather than computer science. So SRAM consists of 6 transistors, 4 for storage, and 2 for access. The key takeaway from this slide is if you look at the number of transistors needed to store 1 bit, this is 1 bit of data, one single bit of data. Compare this to DRAM, it uses only 1 transistor and 1 capacitor. Much easier in terms of the cost, much lower, right? So the charge in the capacitor stores the value. It indicates 0 or 1. And for those of you who might have learned about the property of the capacitor before, unlike the typical like, transistor, when you store things in the capacitor, electron leaks out. Electrons actually leaks out all the time. So one thing DRAM has to do is what we call refresh. This is actually one of the things that limits the size of DRAM because every single right now is 64 millisecond, right? right at that threshold, 64 milliseconds, your RAM has to write the old data on top of it to make sure you can retain the data. Otherwise, you lose the data. So this is what happened in your DRAM, and that's one of the governing factor of how big DRAM can be. So the current DRAM technology, because it uses capacitor, so the question is, you can burn permanent storage on it, not for DRAM. DRAM put charge, literally electrons, into the capacitor, and the property of the capacitor, it actually does leak the electron out over time. So you have to refresh. You have to keep writing over and over and over again. One thing that you might have noticed, what happened when you shut down a computer? Do I have anything left in the memory? If I shut down the computer, where's all my data in the memory? If I unplug the memory and somehow I can probe into that, it will be all gone. It will be all gone, right? These are all gone. Why? Yeah, electrons leaks out. Within 3 seconds, it's all gone. Actually, within like a few seconds, it's all gone. So when you shut down the computer, your data in the memory is gone. You have to commit, basically save anything you have to save to the storage, right? The hard drive and the SSD. That's where you store the permanent data. You can unplug the hard drive, plug it into another computer, data is there, but not with DRAM. Not with DRAM. All right. So again, side topics. I hope this is interesting for you, that you know more about SRAM and DRAM. But here are the trade-offs. Here are the trade-offs. SRAM is faster. So a small SRAM that are less than say 1 kilobytes, that would be really fast. It actually take less than 1 nanosecond. So you're looking at maybe like 4 clock cycle for the current processor. That is like say 3.6 gigahertz, 3.7 gigahertz. It would be around 4 clock cycle. If we have 1 kilobytes, it would take 1 nanosecond, around 4 clock cycles still. If we have megabytes of SRAM, it maybe take 3 nanosecond, 10 clock cycle, right? These are fast, but they're expensive. DRAM is cheaper, but slower. DRAM is cheaper, but slower, right? It uses fewer transistor per bit. And gigabyte of DRAM takes about 12 to 15 nanoseconds to access. So this particular overhead is some of the things that often get overlooked when you write a program, because one thing that many programmers assume, if you haven't think about it much, is, let's say I have an add operation, I have a multiply, and I have a data access. So let's say if you look at the time it takes to do an add and multiply, which one takes longer? The multiply, right? And then if you look at multiply versus data access, you might find out that data access also takes much longer than the multiply. So the code that you write, whatever code that you write, they are not equal. Adding take longer than logical operation, the one that you did in assignment 3. Those are really quick. Multiplying take even more time. Division, way more time. Data access, way more time, right? So be mindful of this thing. Before I go into caching and the content, the remainder content of this lecture, I want to kind of prime you for, hey, since I'm a hardware guy, right? Since I'm more like a computer architect, I want to also talk about, hey, what's coming out? What might be something that you see in the future, hopefully within the next 5 years. So these are things that some of them are already out, such as 2D DRAM tiling. 2D DRAM tiling is used in recent GPUs where you can put more DRAM and much more bandwidth to DRAM. It's perfect for the GPU. 3D stack DRAM is basically improve upon the 2D DRAM. The difference is now you can put the chip on top of each other. Magically, people from material science and circuit work together to allow a method to basically make sure it doesn't heat up and burn the chip. So now you can stack things on top, right? It's actually now on the shelf in many GPU that are high end, like the A100, use the technology called HBM2 or high bandwidth memory. It uses 3D stacked DRAM. Anyone here seen the announcement by AMD on Monday about the server chip? There's a new server processor from AMD. So if you watch the news, but on the server side of things, yes, that's 128 core ones. One thing that you might have noticed, it goes up to 800 something megabytes of cache. This is never ever possible before. It's a lot of cache. They use 3D stacking as well, but they stack the cache. They somehow stack the cache so that now the cache, which used to be something like tens of megabytes, you have now 800 megabytes of cache, total cache, right? I mean, in the current days, a server would revolve around maybe a few hundred of megabytes of cache. Never before you have 800 megabytes of cache. That's a lot, right? And today we'll see the benefit of caching. Today we'll see the benefit of caching. There's also NVRAM. Oh, that's a great question. So there's a question on the chat that says, what's a core in the GPU and the CPU? How should I compare this? You might have heard about the core, right? A core is a processor, is capable of reading the program counter. Remember our old friend program counter? You go check the program counter, figure out what's the instruction, and run it. So that's one core. So if you have multi-core, what can you do is you can run multiple programs for each core, right? You can run multiple programs for each core. The GPU works the same way. You have each core as well. Forget about the CUDA core. That's not a real core. But a GPU core is referred to by the word simultaneous multiprocessor, or SM. The word SM is a GPU core. It's also capable of reading the program counter, understand what the instruction is, run that instruction. So hopefully that clarified things a little bit more. I'm sorry about not going into more details because it actually has a lot more detail going into that. Just think of it as one processor. Each core, yes, each core can be used for each application, or if you have a parallel program, this is called multi-threading, you can run amongst different core as well. For basically each thread would be run on one core. In the GPU, the difference in the GPU is you run a lot of threads in the core. You run a lot of threads in the core. The key difference lies in the hardware side, like how you design the hardware. Yes, you can use multiple core for single application. If you have, say, the application like Photoshop, right? How many people use Photoshop before? So if you use Photoshop, Photoshop can spawn multiple threads to process your image. To process your image, it can spawn 4 threads or 8 threads depending on whatever hardware you have, and it would run on multiple core just to work on that Photoshop image. All right. So this is basically why sometimes multi-core is awesome, because you can increase the speed of the program by spawning each thread so that they work together to finish the program. All right. So hopefully that addressed the question a little bit. Like, what does the core mean, right? It allows you to run a thread on the core. And also there's new technology called NVRAM, non-volatile memory. These are closer to the SSD that you have on the hard disk side of things, right? It's non-volatile, means that data doesn't leak out anymore. It stays there. When you write, the data stays there. You plug it out, you plug it into a different machine, somehow data remain there. These are huge. These are huge. The size of this NVRAM can go to terabytes of data, terabytes of memory. They are more power efficient. It consumes less power, but they are a little bit slower than DRAM. It's actually really fast, but it's still slower than DRAM, a little bit slower. The problem with NVRAM that people are still trying to make sure we have that fixed. I mean, most of the research paper have that fixed, but we haven't really like make a device and sell it in the market, except for the Intel Optane. No, NVRAM is not in the graphic cards. In the graphic cards, they use DRAM called HBM2. It's a different organization on how you build and put together DRAM that will give you a lot more bandwidth. NVRAM is hopefully coming out hopefully in the next 5 years. You might see that. And you will see a lot more capacity. What is in there, the reason why they can have more capacity is you can pack more cells. Like you can put more things on it per the same unit of area. So you can like actually have more capacity. These are different things that both the people in material science, circuits, computer architecture, computer system would have to work together to keep pumping out new and cool devices that works and run on a machine, right? So that's why we can keep pushing new technology. You can also have a hybrid memory. This is more like an Intel Optane. You can have DRAM backed by a non-volatile memory, right? One of the downside, I forgot to tell this, one of the downside of NVRAM is similar to the SSD. One thing that you might have heard about the SSD is if you write to the SSD too many times, it gets destroyed. That is true. Because when the write operation, when you have to write the data to the SSD, it destroys the cell a little bit at a time because you actually shock the cell. Imagine you human being is in an electric chair and someone write the data in, you shock that person, right? The same thing go with NVRAM. You kind of push you kind of shock the cell to make sure they change the state to store the data. So the more you store, the likelihood that the cell would fail, right? So we have to engineer around this downside. If you're interested in any summer projects or anything involving this, let me know. I believe I'm the only one in this country, probably, that looks into these areas and how to architect them. So if you're interested in more like a hardware stuff, more like a system stuff, feel free to check with me, right? My lab has a few projects on this. Exactly, yes. So you might have heard about the QLC and then also the MLC, right? MLC is multi-level cell. So TLC is triple level cell and QLC is quad level cell. What does it mean is instead of having one cell storing 1 or 0, right? One cell store 1 or 0. High voltage 1, low voltage 0. TLC is one cell. I will store 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, blah, 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 up to 1, 1, 1. So instead of storing only 1 and 0, now you store 8 different combination of value. This means that if you write to any of these bits, you need to write on the entire cell. This is a technique to save cost. It doesn't live as long as the MLC, where let's assume MLC is multi-level, so it can be 2, 3, or 4. So let's assume it's 2 bit per cell. QLC and TLC is not going to live as long as 2 bit per cell because they use 3 bit and 4 bits per cell. All right, so yes, the answer is correct. Because when you write to this bit, there's a more probability that you will write more often to the same cell. All right, so these technologies there to save cost. Ideally, if you want to make it as durable as possible, make sure you pick the one that has fewer number of bits per cell. fewer number of bits per cell, right? And there's quite a handful. These days, actually, there's quite a handful of tricks you can do to make sure they last longer. So things would get better and better and better and better. But the key thing is going back to the comment earlier, I don't believe in zero latency because this is true. Memory is slow, right? Memory is slow. Even with the new technology, memory is still slow. Why is that the case? We call this memory wall, actually. If you look at the speed of how fast CPU gets over time, this is like year, right? 2000, 2010, 2020. And this is the speed. This is CPU. It gets faster and faster and faster every generation, which is awesome, right? The same thing goes with memory. The DRAM also gets faster. The problem is it doesn't get that fast. It gets faster slowly. So compared to the CPU, they will not be able to catch up, right? So memory is always gonna be slow compared to the how fast the CPU would go. Right? There's a limit on how fast you can move electrons. Obviously, physics, right? Physics basically control how fast things can be. It just you can't defy physics. That's magic. We don't have black magic. All right. But we do have our brain and we have science, right? We have science, so we can quote unquote from the movie Martian. If you watched it, we can science the shit out of this to make sure memory looks fast. All right. So that's the goal. How can we make sure that memory look fast? From the programmer point of view, you can write fast program. Optimize the program, doesn't use a lot of memory, making sure you hide this slow memory access. This is a common technique. We use it all the time. And this is really great. It's a great tool, right? You can also try to optimize for performance. But the problem is, as things get faster, the size of your data also increase, right? Anyone here heard about this terminology called big data? What does big data mean? Can someone tell me what does big data mean? It's like one of the hype keyword that I don't agree that it's actually a new thing. So can someone tell me what's big data? It's a lot of data, right? It's much more data than your machine can typically handle. Isn't that always true back in the day when we have like 10 megabytes of RAM? I mean, look at the anyone here watch the movie Imitation Game? So if you watch Imitation Game, right, you see that they're trying to build the machine. That machine, there's a name for the machine. That machine is called the Bombay. They were trying to build it to crack the German secret code, right? And what is the data that you're trying to process? It's just a secret code, right? And you somehow have to manage a lot of moving parts, right, to make sure you can crack the code. Now, if you look back, right, yeah, for the Enigma ciphering. Oh, it's called the Bombay. If I'm correct, I think it's called the Bombay, Bombe. Maybe I'm wrong actually. I think it's the Bombay. Yeah, and to be honest, during that day, right? Um, the German also have their own supercomputer. Apparently, they got bombed. I think that's called a machine called C3 that actually get bombed during the war. So yeah, every side built their own supercomputer to make sure they can perform computation. It's always there. Computer is the tool that we use to help, right? To help with our well, back in the days, not daily life, but these days our daily life, right? How many people agree with me that the data that you're having to process is always going to be bigger than what the machine have? How many people have like 10 Chrome application and you somehow see that, hey, things are slow? It's always there. Machine is always having to catch up to the demand from the programmer, right? So big data, to be honest, from my perspective, is a fad. It's a makeup word. It's always there. We, from the system point of view, from the architecture point of view, from the programmer point of view, from the compiler point of view, we have to work together so that we can sustain, right, newer application that can benefit from feeding more data to do awesome things, right? So that's the goal. We want to speed up memory access. How do we do that? Let's be greedy. That's what engineer be. We want to make sure we can get the best of both worlds. We want a fast memory and we want a large memory, right? So the idea is, well, we know there's SRAM that are fast but small, and we know there's DRAM that are slow but big. So we can have multiple level of memory because the observation is DRAM is slow, SRAM is fast. I'm gonna put SRAM close to the processor, a small SRAM that's really fast, next to the CPU. On the same processor, on the processor die, when you buy a CPU, it comes with this SRAM. I'll put L2 and L3 SRAM as well, but they're bigger. Because they're bigger, it takes a little bit more time. And then if your data is not in these SRAM, then you check the DRAM, the main memory. This concept is called the memory hierarchy, right? Well, the reason why they are faster is actually more because they are smaller. It's actually more because they are smaller. We put it next to the processor because it's where you can place the SRAM. But because they are smaller, it's like when you have to search for your friend in a room, right? If the room is big, it will take more time. If the room is small, it will take less time. It will take less time. So a small SRAM typically are faster, right? As technology progress, it would get faster, but smaller is going to be faster than bigger one anyway. And this concept is called the memory hierarchy, right? So you have the CPU core, right? The processor run x86 assembly, load, add, subtract, jump, whatever, right? When you need to access the data, instead of going directly to the memory, it will first check the L1 cache, followed by the share L2 cache. These are typically done in our processor. Then you check the memory. These days you have L3 and L4. Think of it as another layer of bigger cache, a little bit smaller cache. Sorry, a little bit slower cache, but still much faster than DRAM. And this concept is called caching. This concept is called caching. And the way I would compare this caching is I'm going to give this high level overview, right? So let's say I want to make coffee. I want to make coffee, and I need coffee bean to that to actually make coffee, right? So where should I check? Where should I check for coffee? If I say, hey, I'm running out of coffee, which I did, right? I want to make more coffee. Where do I go to? I need coffee bean. Where do I check? Well, I mean, the first place I would check it was check my kitchen cabinet, right? In case I have one store right there, which I did. So the first place I would check my kitchen cabinet. Hopefully, there's coffee bean. So think of register. The register is like your kitchen cabinet. If it's not there, where can I go to? What's the close place that I can go to? The store, right? So I can walk around, check if any store around me have coffee beans. I can go into 7-Eleven, something that's always in every single corner of Thailand street for some reason, right? It's everywhere. It's close by. So hopefully these are fast. I can go to 7-Eleven, find coffee bean, and then I can come back home and make coffee, right? Think of this 7-Eleven like a cache. fast but small, right? 7-Eleven is small compared to say nearby Lotus, Big C, Macro, nearby mall, right? Or even things like nearby coffee shop, they will have more coffee beans for me, right? So think of this as the main memory. Hopefully they stock some coffee bean, right? Hopefully they will stock some coffee bean. If I don't have that in a nearby mall, then I would go to a coffee farm in Thailand, and it's like going to the disk. It's really high overhead, really long process, but I will get my coffee. All right. And then for those of you who use Dropbox or Google Drive, Network Drive is like flying to a farm in Brazil to get your coffee bean. Right? So that's how far each of the steps you have to go to get your data. Is it more clear now that what does cache do? What does cache do? So it's like an intermediate storage that are fast but are small, right? So if I have to run the 7-Eleven, what should be my policy in picking what to stock and what not to put on the shelf? What should be my policy if I need to run 7-Eleven? I would store the most common things in there, right? Things like sandwich, sausages, ham, milk. I am less likely to find coffee beans, to be honest. I don't think I'll find it there. 7-Eleven, right? So you store the most common things like mama and all those like bottled water and like the sweet drinks, right? Caching also have a policy to manage what data should be in the cache and what data should not be in the cache. Same thing, you have to manage them. Memory is where you store all the data, right? So to use the cache, the ISA, your x86 ISA, will not allow you to control the cache manually because that's annoying. You don't want to do that. It's too much overhead to the programmer because you don't want to control this all the time. You cannot access a pointer to cache to a location. You can give the hint to the hardware, but that's it. A pointer in the program can only point to a DRAM location. The modern processor would automatically manage the cache for you because we kind of look at how you write the program and build a policy to determine what should go into the cache and what should not be in the cache. This is done automatically. Some address that you want to access will be in the cache. Some address that you want to access will not be on the cache. Some type of computer would allow software managed cache like the GPU scratchpad. You can manually control this, but it can be complicated because more tasks for the programmer, essentially more tasks for the programmer. There's also this concept of caching applies to things like web cache. Anyone visit a website for the first time and realize that somehow that access is slower than the second time you access the same website again? So your computer actually sometimes store the website information locally on the disk to cache the website that you access. There's also a database. Database also apply caching to cache frequently used data in the fast storage. You can also have the cache the file that used often on your computer in DRAM. So all these techniques apply and the same concept apply. Caching, I want to make sure I put fast, like frequently accessed thing in the fast storage. I access data often, I put that in the SRAM cache. I access data often, I put that in a DRAM rather than the disk. We use this all the time. And now let's talk about some basic terminology. Right? So let's now talk about basic terminology. Recall the store, load, and move instruction. Basically, we move the data around. The cache also has its own unit of the data. So when you load the data, this is a data word, right? One word. which can be 8 bytes in a 64-bit machine. The cache has its own unit of data. It's called cache block. A cache block can be larger than the size of the load. Typically, if you look at the Intel processor, for example, a cache block is 64 bytes. It's 8 words. You put 8 words in there. A block is bigger than a word. Sometimes if you read textbook, it is called a cache line. Exact same thing as a cache block. Cache block, cache line, same thing. Each cache block is mapped to some location of the cache. It's mapped to some location of the cache. And access, when you want to access the data, it's going to go to certain parts of the cache block because, again, your access is to one word. Your cache block contains multiple words, so you need to know what address you are trying to access. When you found the data in the cache, we call this a cache hit. When you cannot find the data in the cache, we call this a cache miss. All right, with me so far? So here's the basic terminology. So let's say you have address A that are in cache block X, and here's your cache. You have cache block Y, cache block X, cache block W, and cache block C. When you access A, which go to cache block X, this is there in the cache, so this is a cache hit because you can find your data inside this cache block X. So that's the basic terminology. Address is mapped to a certain cache block. If the cache block that you want to access is in the cache, it's a cache hit. Otherwise, you go to DRAM. We'll go to the next level of the cache. In order to determine whether my data is there or not, what information do you need? Obviously, you need to store the data in the cache, right? Otherwise, the cache is useless. You need to store the data in the cache. To be able to look up the data, what else do we need? You need to make sure that from the address, right, you can find the data using some key from the address. I would use that to say, hey, is that my data? Is that someone else's data? Because when you look at the inside of the cache, there are mainly two things in there. The tag store. So this is your key. This comes from a part of your address. This comes from a part of your address. This is where you store all the tags associated with the memory address. And when you have to access the data, you use this tag to search. And then the cache also has to contain the data store. This is where you store the data itself, right? And to search for the data, parts of the address is used as that'll be broken down into 3 separate regions. Part of them is called the index, part of them is called the tag. We will go into more detail. We will now go into more detail. What is the index and what's in the tag? But before we go into more detail, let's look at the overall organization first. Let's say you see in the spec sheet say 4 megabytes of cache. What does it mean? What does it mean? So a cache can contain multiple blocks. Each block can contain your data. Each block can belong to a cache set. What is a set in mathematics? A set is used to store, a set is used to store your data. So each memory address basically would be mapped to a certain set. So let's say you have a cache that has 7 sets and 2 cache blocks per set. This is a configuration that the hardware would give it to you. The hardware has this configuration. In this case, let's say you have 8 sets, 8 sets, 2 cache blocks per set. With this, how many total number of cache blocks is in the cache? How many total number of cache blocks is in the cache? I have 8 sets. Each set has 2 cache blocks. 16, right? So now you have 16 cache blocks. So let's say each cache block is 32 bytes, then the size of this cache is basically 16 multiplied by 32 bytes. So with me so far, basically this is how you can manage the cache. So visually it looks like this. Let's say I want to access cache block 4. Let's say I want to access cache block 4. I have an address that want to access things in the cache block 4. From the address alone, you can tell that the set is in set 2. There will be a part of the address that would map to set number 2. Then you use the rest of the address to check, hey, is that my data or not? So a quick example. Let's say you have 1024 byte cache, 32 byte cache block, and for each set there are 8 sets in total. How many cache block per set do I have here? To calculate this, basically the total size, right, of the cache is going to equal to number of sets multiplied by the size of each cache block multiplied by the number of cache block per set. So 1024 equal to number of sets is 8. The size of cache block is 32. The size of a number of cache block per set is n. Basically, then in this case, you have 1024 divided by 32 multiplied by 8 cache block per set. So I can give you a different number. You can also check out the processor specification and then figure these things out. Why is that good? When you know this, you can write a program in such a way that it would hit in the cache all the time. That's totally possible. We'll go into more detail in the PCSA class in the next semester. All right. But here's the basic idea. What we want to focus on today is more like, I have an address. I need to figure out, is my data in the cache or not? So data in DRAM is going to be much bigger in the data than the data in the cache. And you cannot store everything in DRAM inside my cache, right? So the process of accessing the cache involves the lookup process. See if my data is in the cache or not. I just need to check if my data is in the cache or not. So an address can be divided into multiple set of bits. Part of it is called the index bit. Index bits correspond to the set ID. Index bit correspond to the set ID. It tells you, hey, the set ID is this. Go look up the set number 6. So let's say my index bit is 1101. What's my set ID? 1101. What would be my set ID? This is basically 8 plus 4 plus 1. That's 13. So you go to set 13. You will know that if the index bit in this case, let's say it's 1101, you would go to set 13. If the index bit is 1010, what's my set number? What set do I go to search for my cache? Set 10, right? Then once you know the set, there can be multiple cache blocks in the set. You then use the tag. You can use the tag to check, hey, is that my data or is that someone else's data? You use the tag to check if that's your data or is that someone else's data. All right. So let's say over here you have a cache, right? And they say this is set number 2. You have cache block A with the tag X, cache block B with the tag of Y. You have an address that apparently the set ID is 2, the tag is W. Is that a cache hit or not? For this address, the address, I look at the address, I got the set ID to be number 2, you go to set 2, then the tag is W. Can I find this in my cache? Right now I have two cache blocks. One of the cache block has a tag X, the other one has tag Y. I want to search for tag W. No, right? In this case, it's a cache miss. You would then go to DRAM. What would happen is you would go to DRAM. In this case, it's a miss. Then you go to DRAM. You get that data. You get whatever data that comes in here. Let's say it's cache block C with the tag W. Then you comes in and say, hey, I will pick one of these blocks. I'll kick it out. And then I will replace it with the new cache block I just accessed. And now let's say you're in a loop and you access this same address again. Is this a hit or is this a miss now? You access the same address again. It's now a hit, right? Because you just brought in the new cache block. So this is how cache operate. Next week, we'll learn how do we pick which one to kick out. We will learn how to pick which one to kick out next week. This week, today, we'll learn more about, okay, how do I figure out the index bit? How do I figure out the tag bits? So the next slide, we'll talk about how to get the index bit. The first thing you have to understand is each address, right, point to a unique byte. So let's say I have a cache block. It contains multiple bytes of data. Usually in x86 machine, it's 64 bytes. So the last n bits are reserved so that I can tell. So if you look at my cache block, right, this is my cache block. You can have byte 0 up to byte 63, right? This is byte 0, this is byte 63. My address can go into any of these bytes. I can go to any of these bytes. So I need to be able to tell that, hey, the address I'm trying to access is right here in byte, I don't know, 13, for example, in byte 13. I need that ability. So the last n bit of my address, so let's say this is my address. This last n bit would correspond to what byte am I accessing. So let's say I want to access byte 13. What should go into that n bits? I just want to make sure I can point to byte 13. So what should go into that last n bit? And this, again, let's assume it's 64 byte for the cache block. N is now correspond to log 2 of 64 because I need to be able to tell each individual bytes in there. I want byte 13. 13 is what in binary? 13 is what in binary? 1101, right? So over here it's just 1101, and because you need 6 bits, the other 2 bits are 0. So that would go into the last 6 bytes. If my cache block is 64 bytes, if my cache block is 32 bytes, it will be just the last 5 bits. Then let's say you have let's say you have 16 number of sets. How many bits do I need to tell between set 0, set 1, set 2, set 3, set 4, up to set 15? How many bits do I need to be able to tell the difference between set 0, set 1, set 2, set 3, set 4, up to set 15? If I have 16 sets. It's log of 16, that should be 4. Log of 16 is 4. right? Just to double check the reason 5 is actually I want to be able to tell from 0 to 15 because I have 16 set. The set goes from 0 to 15, and you need 4 bits for that. Right? You need 4 bits for that. These bits are called the index bit. So let's say in this address, my index bit is 0110. What set do I go to? What set do I go to? If it's 0110, what set do I go to? 6. Yes, that's it. You go to set number 6 on your cache. Then the rest of this are the tag. The tag would tell, I go to set number 6. Is that my data or is that someone else's data? You would check the bits here. If the bit match is a cache hit, it means that that's your data. That's your cache block. All right. Are we clear so far? Yeah, tag. Oh, I mean, this whole thing is a pointer. It's an address, right? This whole thing is a pointer. We only need the tag to tell whether it's a data or not, because that is guaranteed to be unique for each, I guess, each individual address you're accessing. So it does feel like a pointer to some extent, but it's more like a key, right? It's a key to check, is that your data? The purpose of a key is to check, does it match with the lock? Yes, and that's, yes, this is the address I show is, this is your pointer, this is the address of my data. Everything here comes from the address of your data. So everything you use to search for the cache comes from the address of your data. All right, is it more clear now? Basically, you have a pointer. The pointer has some address, right? That address will be broken down into the last n bit would tell me which byte in the cache block I'm trying to access. The next m bit is the index bit. Go to the set number that I have in there. The rest are the tag bits. All right. So now let's do a quick 5-minute break. We'll come back around 3:20 and we'll resume the discussion on different organization of the cache, mostly governing how many cache blocks should be in one set. So let's do a 5 minutes break. All right. We'll resume from this slide. I'm going to keep this slide up in case you want to absorb this a little bit, and in case you have any additional question, because this is one of the key slides that I want to make sure you understand. It also has a lot to do with your lab, your assignment 4. If you get this, the assignments will be much easier. If you didn't get this, you need to get this until you can do assignment 4. All right. So we'll do. I'll pause the video for a bit. We'll resume in 5 minutes. Oh, the last end bit, great question. So let me do this before we take a break. Because each address is to each individual bytes, right? Each address to each individual bytes that I want to access. The cache block is big. It contains multiple bytes. So that last n bit just tell me which byte in my cache block. Is it this byte, or is it this byte, or is it this byte? Is it more clear? Basically, it would tell you which byte am I accessing. All right. Yeah, so once you draw this out, it's actually really easy. But before you draw this out yourself, it looks really intimidating and confusing. So my recommendation, I will have another example toward the end of this class to show like what would happen. Let's say I have this address and here's the content of the set. Is it a hit or is it a miss again? So we do that after the break. Let's do a 5 minutes break. We will resume at 3:20. All right. Okay, so before the break, we were talking about the notion of how to find the index bit and how to find the tag bits, right? There's also the notion of how many cache block do you want to put in the set. So if you read a classic textbook on computer organization, computer architecture, or computer system, you might have seen this name called a direct map cache. A direct map cache is actually really simple. The way you think about it is one cache block per set. One cache block per set. So to search for your data, you have an address, right? Because you run the program, you know the address. The address that comes in, you extract the index bit. You would extract the index bit. That becomes the set ID. The set ID go to the correct set. You then check the tag. If it's your tag, it's a hit. If it's someone else's tag, it's a miss, right? It's as simple as that. If it's hit, it returns the corresponding data. Otherwise, you search the next level of the cache. So my lasting question about this is, can I write a program that, let's say I have unlimited cache size, but I would write a program in a way that we get 0% hit rate. We get 0% hit rate. Basically, I have access to A, then to B. These are address. These are pointer. A, B in a loop, right? A, B, A, B, A, B. And let's assume that A has tag Y, set number 2. B has tag X, also set 2. Also set number 2. So if you look at the cache, right? These are my cache. There are multiple set, right? This is set 0, set 1, set 2, set 3. And let me also draw another row to specify here are the tag. And this is the data, right? So I have access to A, B, A, B, A, B. The first access would bring in the cache, right? Would bring in the cache. What's the tag for the first access to A? What's the tag? What's the tag of A? Y, right? So it goes to set 2. So I put the block for cache A, I mean the access A, whatever cache block that is, I put that in set 2. The tag is Y. Now I have the next access. I have the next access to B. So what's the tag of B? The tag of B is X, right? Is that a cache hit or is that a cache miss? So to answer that, you would ask, is the tag similar? It's not, because one is X, the other one is Y. So this is a cache miss. You would then go to DRAM to get address for B. And then what will happen is, in the direct map cache, right? Now that it's a cache miss, you would get rid of what is the old block here and replace it. You would replace it with B. And what's the tag for B? B is tag X. What's my next access? So we are done with this. We're done with this. The next access is to A. What's the tag for A? And is that a cache hit or is that a cache miss? It's also a cache miss, right? Because tag for A is Y, and the tag in the cache right now for set 2 is X. It's a different tag. So I'm going to kick this out, replace this with cache block for A, and put the tag Y in here, and we're done with this. So will we ever get a cache hit? Oh, you mean why do we replace the old block in the cache, right? So the question is that a question? Oh, okay, awesome. Actually, I forgot to tell you one more thing. This is the main property of caching, right? So one of the things that when we design the cache, one of the things we observe is there are a lot of reuse in your program. It's likely that if you access something, you are likely to access the same thing again. So in this case, you access B, you want to make sure B is now in the cache. And because B mapped to set number 2, I would kick out whatever is there and replace that with B. Is that more clear? So in this case, I access to B, A is in the cache, and the cache think that I'm more likely to access B, right? And I put X in here. First in, first out is one of the policy, actually. It's one of the policy that you can use to manage how do you maintain this cache block. And let me be honest here. Please consider unlocking the restriction about the hardware. If you put in the hat of like, I'm the hardware designer, this thing you can design. You can actually design what to do here. By default, the computer that you have, if they use direct map cache, they will be kicking things out. They will be kicking things out. But I mean, you can choose to not to do that, right? Depending on your hardware design, that as an engineer, you can do it. As a computer scientist, you can propose the design too. So it's your choice. In a real computer that you buy in the market right now, if they use direct map cache, it would kick out based on this pattern, right? Why do we do this? Because we observe that when you use a variable in a program, you tend to use the same variable again really soon. So we would apply this technique. So is it more clear about direct map cache and this example? And this example would mean that we never get a cache hit. We never get a cache hit. So what can we do to improve this design? Can someone suggest some modification that I can do to improve this design? So right now it's one cache block per set, right? Oh, okay, awesome. That's a great that's a great answer. That's actually quite a lot of paper. Some of them is really, really, really high impact actually that propose to, well, why don't you read ahead of time, right? And figure maybe you can bring more things in. So it's one of the really, really legit techniques. It's actually not directly to solve this problem, but the benefit is actually for a different purposes. Its benefit is actually to make sure I have new data coming in ahead of time. In fact, some of the idea actually was proposed by my own advisor. He just got the Test of Time award. That paper that basically is called Run Ahead Execution would basically read ahead of time to bring the data into the cache, and it makes such an impact to the industry that he just got the Test of Time award. It's an award to a paper more than 18 years ago that make a huge impact to the industry. So yes, great idea for sure. Great idea. What else can we do? What else can we do? Can we add more cache block to a set? Can we add more cache block to a set? By the way, this is why I love asking you guys questions, because typically your idea make a lot of sense, and these ideas actually work. So, but because I need to lead into the next slides, right? Because I need to lead into the next slide. One thing I can do to improve this is I can then, instead of having one cache block per set, right? I will have multiple cache block per set, right? I would have multiple cache block per set. So the key idea of a set associative cache, a key idea of a set associative cache is I would have multiple cache block per set. It will be in the same set. So let's say I have 4 cache block, right? For A, for B, for C, and for D, and my access to A, B, I'm sorry, A, B, A, B, A, B, right? In this case, I would get 100% cache hit because now I can maintain both A and B in the same set. Set number 2 I have earlier, right? This is called the set associative cache. This is called the set associative cache. The main idea is have multiple cache blocks per set. All right. And most of the time, just when you read the processor specification, like when you go and buy the Intel chip, you might have seen it say 4-way set associative cache. This number basically tells how many cache block is in the set. 4-way mean I have 4 cache block. 8 ways mean I have 8 cache block. What are the downside of this? You now need to search, right? Because let's say you know it's set number 2. Now you need to check, is it A, is it B, is it C, is it D? You compare the tag. So that's a potential downside. You have to compare the tag to make sure to check whether your data is there or not, right? I would use this example, right? I know it's COVID. Maybe you haven't gone to a movie in a long time, right? But let's say you go to a movie theater. What would be on your ticket, except for the name of the movie? What else should be there at the time, right? Sure. The seat, right? The seat, the row, right? The row number and the seat number, right? So let's say it's a movie ticket, right? You have the seat and the row number. So think of it this way. What is the first thing you would do when you walk into the movie theater? Do you go to the seat letter first, or you go to the row first? You go to the row, right? So think of the row as your set ID. Then the seat is your tag, right? You better make sure you sit in your seat, right? But you first go to the row. That's the reason why there's a row is, what if there's no row ID? What if you have a movie ticket and it comes with the seat number, and the entire theater would run from seat 0 to seat 500? What would you do? Would it be annoying because you don't even know what row you're in? You have to somehow walk through the whole thing, right, to find the correct row. So think of the set ID as the row number. It would tell you what row you have to go first. Then you walk through the row to find your tag. The tag is the seat number. Once you solve the correct seat number, that's your seat, right? So that's your tag. Hopefully this analogy make it much more clear that you have the row and you have the seat, right? And then now that we talk about set associative cache, you can go to the extreme. It's called fully associative cache. Anyone want to take a guess what it means? Anyone want to take a guess of what does fully associative cache mean? Actually, it's more like I have one set and I search the entire thing. This is similar to a theater with no row number. I just only have the seat number and I search the entire theater. All right, so that's a fully associative cache. The number way is the number of cache blocks that you have. You have everything in one set. You search. You full-blown search everything. You need to do a lot of search inside the tag store. So that's the downside. The upside is you're not likely to run into this collision to the same set, right? So let's do some example for cache lookup. And because I'm hungry, yay, I'm sorry, I am hungry. I would use my address beef. Can someone type in the binary for beef while I will basically talk about the configuration of my cache so that we can go through the example. So let's say I have 4-way set associative cache with 32 byte cache block and 8 set. And thank you. So Binary of this is 1011, 1110, 1110, and 1111. Now let's go through this together. Let's get the first thing, byte in block bit. How many bits do I need for the byte in block bits? To do that, you would go to the size of the cache block, which is this guy. You do log of 32. What's log of 32? 2 to the what gave you 32? 5. Yes, thank you. So byte in block bit is 5 bits. So in this case, what is my byte in block bits? It's the last 5 bits, right? So what are those? I just circle that for you. Can someone type it in? 0, 1, 1, 1. Yeah. So this is literally this is your pointer, right? From your pointer, let's say my address is 0xb. I would now I can tell exactly where is that in the cache by doing first thing, get the byte in block bit. The next set of bits is the index bit. What's my index bit? How many index bits are there? You look at the number of sets and you put log of that. You put log of that. What's log of 8? 3, right? So it's 3 bits. This is 5 bits. So 3 next bit, this is byte in block. This is my index bit. So what's my index bit? 111. So the set ID is what? What set do I go to? 7. Yes, thank you so much. And what's my tag bit? The tag bit is the rest of my bits. So over here is the tag, right? This is 1011, 1110, right? So let's say this is the content of my set 7 at the moment. And I'm gonna use a different color to kind of specify this is the tag, this is the data, this is the tag, this is the data. And let's say the tag over here is 0x11, 0xba, 0xbe, 0xd, I don't know, d0. And this is data is x, y, c, and w. Can someone tell me, is this a cache hit or is this a cache miss? And if this is a cache hit, what is the data that you're trying? What is the data inside the cache block? It's a hit. Why can I know it's a hit? Your tag over here, this is B, this is E, so my tag is BE. I would then go and check, hey, is BE in here? Apparently it's right there, right? So it's a hit. And you grab this whole thing, so this is C, but this C is actually 32 bytes, right? It's the entire 32 bytes. So in this case, your address beef, make sure you get these 15 bytes of this C. You get the 15 bytes because your byte in block bit tells you that's 15. So you go to the 15 bytes and you access it. Is it more clear? Is it way more clear now that you see from pointer all the way to whether it's a cache hit or not? Any questions about this? Oh, the last thing about 15. Yes, sure. So our pointer, right? The pointer basically it point to the exact byte of data, right? You point to that one byte of data. I mean, it can be 4 bytes, 8 bytes, depending on the data type, but it starts somewhere. It's gonna start somewhere. So the address beef that has the last bit being 01111, it means that once I have the cache block, I'm going to access byte 15. I'm going to access byte 15 because the address says so. The address tell me I'm going to have to access byte 15 inside this cache block. Is it more clear? Is it now? Yeah, so basically the byte in block tell me which exact byte that you are accessing. And this is actually, again, as I told you, the concept of caching sounds complicated, but in reality, once you know the system, how it works, it's really simple, right? Why simple? Hardware has to be simple because we want to make a cheap computer. Great question. For this pointer, is it only for 1 byte of data only? No. Depending on the pointer type, you will know, do you get 1 byte, 2 bytes, 4 bytes, or 8 bytes, but it has to start from byte 15. So if it's 4 bytes, it will be byte 15, 16, 17, and 18. If it's 8 bytes, it will be 15, 16, blah, blah, to 23. No, 22, I think. And if it's only 1 byte, then you go to byte 15. Is that more clear? All right, so that's actually it, right? This example is really important for your assignment 4 because you would do something almost similar to this, but it would be full-blown working cache. You're gonna write a program that simulate the cache, right? Hopefully you're excited about it. It's actually not hard, but I also would make sure that this year I'll make it easier to debug things compared to earlier years. Earlier year, we asked you to do a cache that's a way too big. This year I'm gonna make it smaller, so when you debug, it's much easier. All right. Uh, so